Good evening. Before I begin, I will play you two pieces of computer-generated music. First, here's the first piece on top. And the second piece on the bottom. So these two pieces of music were generated by neural networks, which were trained on symbolic musical data. Both pieces share the first bar, which comes from a human-composed Irish tune, and is used as a starting seed for the network. The networks were trained on the same musical corpus of Irish folk tunes, the only difference being the form of the data, or else its encoding or representation. The first example, with its repeated first bars, hints at an AAB structure, while the second sort of drifts between disconnected phrases. How many of these perceived differences are due to the encoding of the initial data, and how many due to other factors or even just chance? This is our main research question. Does the encoding of musical data influence music generation, and which is the best way to systematically study it? To answer this question, we limit our scope to sequential representations of monophonic music, and we study a well-established method of music generation. We want to study the encoding's effect on the generated music, as well as the difference in internal representation, what the network understands. For this purpose, we chose to study three types of encoding, which are widely used in music generation systems. Timestep-based or fixed timestep encodings is where each token in the sequence has a predefined time length, given by the resolution. It uses three types of tokens. Notes start with a note-on token and rests with a rest token. Held notes are represented by a same as before token added for the duration of the note after the note-on or the rest token. A problem with fixed timestep encodings is that sequence length increases with resolution, so it becomes memory intensive when we want to encode more expressive music such as a real-time performance. One way to solve this problem is to move to what we call an event-based encoding. Here we also have note-on events and a separate note-off for each node, but here time is handled by special advanced time tokens, which, as their name suggests, advance time forward by a fixed amount. This puts a lower and upper bound on sequence length depending on the number of nodes. The last encoding we used is a popular text-based encoding, used mainly in the folk music community to transcribe and share melodies. We used the tokenized version instead of feeding the network character by character, by grouping characters in musically meaningful tokens. We used the shallow one-layer network, mainly because fewer parameters are easier to visualize and understand. We used the dataset of Irish folk tunes in the ABC format, used to train the folk RNN network, of which only the tunes in the key of C with a time signature of 4 quarters were chosen. In every step, we try to keep everything as simple as possible in order to focus on the effects of the encoding. After re-encoding and processing our dataset, we already see a major difference in the distribution for data for each encoding. The timestep-based dataset is heavily skewed towards same as before events, something that gets worse as the resolution gets finer. Note-on events and rests are depicted in blue, their frequency on the y-axis on a logarithmic scale, while same as before events are the bar in red, occurring 2 orders of magnitude more than all other events. The event-based dataset is also somewhat skewed, with advanced time by 1/8 of a quarter being an order of magnitude more prevalent than all other events. Other than skewness of distribution, the sequence length needed to encode a phrase changes between the encodings, making them sometimes difficult to compare side by side. To compare the musical output of our network, we used the standard musical measures widely used in musicology to analyze symbolic musical scores. We compared 200 generated pieces from each encoding dataset with the original tunes whose first bar was used as seed for the pieces, using statistical methods in the literature. In our case, the approach did not show consistent results. When comparing measures in a macro scale across datasets, it looks like all the networks produce music more or less similar to the original dataset. We decided to first look at the network output and gain some intuition as to where the differences lie. One observation, consistent with the examples at the beginning, was how the ABC outputs seem to count consistently better and have more long-term structure. To investigate this further, we visualized some of the network parameters while it processed a piece it had not seen before. On top, we see the network input in ABC notation without a header but with a start song token. In the middle, we see a visualization of the 32 LSTM neurons, with yellow being more activated and dark blue being less activated. On the bottom are the top 5 predictions of the last dense layer, ranked by probability, yellow denoting a higher probability and dark blue a lower one. Looking at the activations, we see that the network has learned to recognize bar lines and the start symbol, and looking at the predictions, we see that it can also anticipate new bar lines with a very high probability, indicating an ability to count. When looking at the activations for the event-based network, we see a different picture. As there are no explicit bar lines in the encoding, we have marked each measure in a different color here, with 500 being the start song token. There is a general block pattern every 3 tokens which we can interpret as the network noticing when to start and stop each node, meaning that it has understood local characteristics of the encoding. It sees a node on event, so it knows what follows is an advance time event and then a node off event. It is fairly certain in its predictions for both those tokens, while when predicting a new node, the probability is divided between different node on events, allowing variation. The same local behavior is evident in the fixed time step train network. Here it's also evident by the size of the same as before blocks that the network has learned to mostly output 8 nodes, which is the most prevalent duration in the original dataset. So can we now answer a research question? Our research shows significant influence on encoding on neural network music generation, but determining and quantifying this influence can be difficult. This is because in a complex music generation system, it is difficult to isolate the encoding's effects, especially if it's vital to the design of the network. Translating data from one encoding to another losslessly is also difficult, either because it is theoretically impossible or there is no available software that can handle the task. Lastly, evaluating generation systems in general is non-trivial, especially with music that has no universal semantic content. An obvious continuation of our research includes varying the dataset and model used, but also trying to design new encodings that can be suited to specific tasks. And that's all. Thank you for your attention, and I move on to any questions you have.